Open the Horten Ho 229 and the future stares back. No pistons, no propellers, only two Jumo 004 turbojets. They did not spin, they roared. They swallowed air, lit it on fire, and spat it out as pure power of nearly 4,000 pounds. Enough to push a bomber past 600 miles per hour. By the early 1940s, Germany's Luftwaffe was losing the skies it once dominated. At the start of the war, it had shocked the world with fast, modern aircraft like the Bf-109 fighter and Ju-87 Stuka dive bomber. But by 1943, the situation had changed. Allied bombers arrived in massive formations, shielded by long-range escorts like the P-51 Mustang. Germany's piston engine fighters were outnumbered, and even when they fought bravely, they could no longer tip the balance. The Luftwaffe needed a miracle. Its leaders turned to new technology, specifically jets. The Messerschmitt Me-262, the world's first operational jet fighter, had already shown what was possible. But the Air Ministry wanted more than a fast interceptor. They needed a bomber that could carry weapons and still outrun anything in the air. Enter the Horten brothers. Reimar Horten, the visionary designer, and Walter Horten, the pilot, believed the answer was simplicity. Build an aircraft that was all wing, no fuselage, no tail. Less drag meant more speed. Less weight meant less fuel, and fewer materials meant easier construction. But speed alone wasn't enough. The Hortens knew the age of the propeller was over. To survive, their aircraft had to embrace jet power. What they created was the Horten Ho-229, a radical flying-wing jet bomber. But it never advanced beyond the prototype stage, leaving its promise untested in real combat. Horten selected the Jumo 004 turbojet, the same engine used in the Messerschmitt Me-262, the world's first jet fighter. To understand its importance, let's break it down simply. A turbojet works by sucking in the air through the front and squeezing it in a spinning compressor. This air is then mixed with fuel and ignited. The explosion creates scorching gases that rush backward, spinning a turbine on their way out to keep the compressor turning. The rest of the gases blast through the nozzle to create thrust. What made this so revolutionary compared to piston engines? Propeller aircraft lose efficiency at high speeds because the propeller blades themselves drag against the air. Jet engines remove the propeller entirely, delivering smoother power and far higher top speeds. They also allowed rapid climbs that piston fighters struggled to match. In essence, jets unlocked a whole new flight regime. The Jumo 004 wasn't huge by modern standards. Each one produced about 1,980 pounds of thrust. But with two buried inside the Ho-229's body, the aircraft could approach 600 miles per hour, almost 150 faster than the P-51 Mustang, the Allies' best fighter. For 1944, that was astonishing. A flying wing with jet power gave the Ho-229 a profile unlike anything else in the war. It looked alien, sounded terrifying, and it promised to outrun anything that tried to catch it. Here's a question. If the Ho-229 had been built in numbers, could it have outrun Allied fighters and changed the bombing aircrafts? Drop your guesses in the comments and we'll come back to that at the end. For all its brilliance, the Jumo 004 was fragile. Germany lacked the rare metals like nickel and cobalt needed for heat-resistant alloys. As a result, the turbine blades were made of cheap steel. They cracked and warped under heat. Most engines failed after only 20 to 25 hours of use. This reliability issue was worsened by Allied bombings on production factories, forcing engineers to cut corners in production. Engines left the assembly line with inconsistent quality, and pilots often went up in the air, unsure how long their power plants would last. Fuel was another problem. The Jumo devoured nearly 1.25 liters of kerosene every second at full power, draining its tanks quickly and limiting the Ho-229's range to about 600 miles. That was enough for defensive interception, but not enough to strike far into Allied territory. Pilots also had to treat the throttle gently. A sudden push could stall or even destroy the engine, a risk that caught out many inexperienced flyers. Despite its flaws, it pushed aircrafts into an entirely new age. The Hortens didn't simply bolt the engines under the wings like the Me-262. Instead, they buried them deep inside the fuselage. This gave the Ho-229 a smooth, clean profile with less drag and more speed. But this integration came with complications. Cooling was harder and mechanics struggled with accessibility. Yet aerodynamically, it was a stroke of genius. By hiding the engines inside, the aircraft presented fewer surfaces to radar. Though stealth wasn't an official science yet, the HO229 stumbled into it. The airframe itself was just as radical. Aluminum was scarce, so the Hortens built the wings largely from laminated plywood, bonded with charcoal dust and resin. Decades later, tests suggested this material may have absorbed radar waves. That means the HO229 was not just fast, but it may actually have been the world's first stealth bomber. The HO229V2, the second prototype, flew in December 1944. It reportedly reached nearly 497 miles per hour at medium altitude. Faster than any Allied fighter of the time, it seemed to prove the Hortens right. But victory was short-lived. On one test flight, an engine failed. The prototype crashed, killing the pilot. Engine unreliability remained a constant danger. Even so, the aircraft's speed and stability impressed observers. Imagine a bomber carrying 2,000 pounds of bombs and outrunning any escort sent against it. For the Allies, it would have been a nightmare, but time was running out for Germany. Resources dwindled, the war collapsed, and the HO229 never advanced beyond a few incomplete prototypes. The HO229's construction was just as fascinating as its engines. Wood made up most of the aircraft. Laminated plywood panels were glued together with resin that contained charcoal powder. This made it strong and possibly radar absorbent. There were also practical advantages. Wood required less industrial machinery to work with, so small workshops could produce parts. Repairs could be made quickly in the field using simple tools. In many ways, the HO229's use of wood was as much a clever wartime solution as a technological innovation. Flying a traditional aircraft meant relying on the tail to keep it steady. The HO229 had no tail. Its flying wing design gave it speed and efficiency, but it also made the aircraft far less stable. To manage this, the Hortens built in carefully shaped wing edges and split flaps that doubled as air brakes. These helped the pilot control roll and yaw, which is the side-to-side balance of the aircraft. But unlike modern flying wings, the HO229 had no digital computers to smooth things out. Every correction had to be made by the pilot's hands alone. Test flights showed that the design could be flown, but it demanded skill. Small mistakes could send the aircraft wobbling or diving. In the 1940s, the HO229 was pushing the limits of what a human pilot could handle unaided. By spring 1945, Allied troops were closing in on Germany. At the Gotha factory, American forces discovered HO229 prototypes and parts. One was shipped to the United States, where it survives today at the Smithsonian's Udvar Hazy Center. American engineers studied it carefully. They were struck by the clean wood and charcoal construction and the concealed engines. Operation Paperclip brought German jet scientists to the U.S., where their knowledge accelerated jet research. The HO229 never flew in combat, but the fact that it reached prototype stage in the chaos of 1945 was extraordinary. The HO229 was more than a failed experiment. It was a preview of aviation's future. Its integrated engines inspired later stealth concepts. Its flying wing shape was echoed decades later by Northrop's designs, and its plywood structure foreshadowed the composites used in modern stealth aircraft. In the 1980s, when Northrop engineers built replicas to test its radar cross-section, they confirmed that the HO229 was harder to detect than conventional designs. The idea that a prototype from 1944 could already possess stealth-like qualities stunned researchers. The B-2 Spirit stealth bomber, which first flew in the 1980s, looked like a direct descendant of the HO229. Its smooth shape, buried engines, and radar-absorbing skin all mirrored principles pioneered, intentionally or not, by the Hortens. The Jumo 004 also left a mark. Its design influenced early Soviet and American jet engines, launching the world fully into the jet age. So let's return to that question. Could the HO229 have outrun Allied fighters and changed the bombing war? In theory, yes. In reality, no. The engines were unreliable, fuel was scarce, and Germany was collapsing. The HO229 was a vision of the future trapped in the wrong time, but it still remains one of the most remarkable prototypes ever built, a machine that foreshadowed stealth and demonstrated jet power. The B-21 Raider can slip past radar, cross oceans, and strike without warning. None of that happens without its engine. The most secret part of the plane, built to be efficient and almost impossible to track, this power plant is rewriting the rules of stealth. When the Air Force started planning the B-21 Raider, the mission was clear. Build a bomber that could fly anywhere in the world, carry both conventional and nuclear bombs, and do it all while staying almost invisible to radar. The aging B-1s and B-2s had served their time, but new threats demanded something smarter, stealthier, and longer-ranged. That's where the Long-Range Strike Bomber program came in, and with it, the B-21 was born. Northrop Grumman designed the sleek radar-evading airframe, but the real make-or-break challenge was the engine. The B-21 runs on two next-generation turbofans, derived from the PW1000G family, designed to combine power, fuel efficiency, and silence, carrying the bomber thousands of miles while masking its heat and noise signature. And it had to be rugged enough to survive combat deployments around the world. Design work kicked off around 2015. Engineers spent years tweaking every detail, from turbine blades to coatings, to make sure the engine met impossible requirements. Then came November 10, 2023. The first B-21 lifted off from Palmdale, California, and landed at Edwards Air Force Base, proof that the design wasn't just theory. And by September 11, 2025, a second Raider had joined the skies, showing this engine isn't just working once. It's repeatable, reliable, and here to stay. Alright, now let's talk about the engine itself. The heart of the B-21 Raider. Remember, the official details are classified, but aviation experts point to a next-generation turbofan derived from Pratt & Whitney's geared turbofan family that powers planes like the Airbus A320neo. For the B-21, engineers adapted it into what's known as the PW9000, with analysts estimating a 4-to-1 bypass ratio. In other words, 4 times more air slips around the core than through it, enough to stretch range and hush the exhaust, without the giant fan that would light up enemy radar. The Raider runs on 2 of these engines, each believed to produce around 17,000 pounds of thrust. Together, they give the bomber the legs to cross oceans without constant refueling. But it's not just about raw power. These engines are built to match the bomber's mission. Sustained high subsonic speeds, efficient long-range flight, and near-silent operation to stay undetected in hostile airspace. And the engine is modular, meaning key components can be swapped out individually, keeping the aircraft in service with minimal downtime. That modularity is what makes the Raider not just powerful, but sustainable in real combat operations. This isn't just propulsion. It's a stealthy, long-range powerhouse, the beating heart that keeps the B-21 flying unseen, fast, and ready for anything. So we know what powers the B-21. Now the bigger question, what makes an engine like that possible? It all comes down to the stuff it's built from. Pick the wrong material and the whole system fails. First up, titanium. It's strong, light, and heat-resistant. That's why you'll find it in the fan blades and compressor stages, the parts that spin like crazy at the front of the engine. Sometimes engineers blend it with advanced composites to save weight without losing strength. Deeper inside, the conditions get brutal. Turbine blades face temperatures hotter than molten lava. That's where nickel-based superalloys rule, exotic metals engineered to hold their strength while glowing red-hot. On top of that, ceramic thermal barrier coatings act like heat armor, protecting metal from extreme temperatures and erosion. Finally, stealth isn't just about shape. Even the exhaust and casing use special alloys and design tricks to reduce infrared signatures and damp mechanical noise. Tiny design choices, a cooled cavity here, a layered shield there, add up to a much harder to detect engine. Put it all together and every piece of metal in this engine has one mission: keep the bomber alive, efficient, and invisible. But how do you actually turn titanium, nickel alloys, and ceramics into a machine that can survive combat? Time to go inside the factory. Let's start with the turbine blades, the engine's hottest, most stressed parts. At full power, exhaust gases can top 1,500 degrees Celsius, hotter than lava. These blades aren't simply cut from stock metal. They're grown through a process called single crystal casting. Molten superalloy is poured into ceramic molds that guide the crystal structure as it solidifies, creating blades with incredible strength to survive heat and stress that would destroy ordinary metals. Up front, the compressor's blades and casings begin life as forged titanium. After forging, they're milled on CNC machines to exact tolerances. We're talking down to fractions of a millimeter because even tiny airflow errors can cause stalls or efficiency losses. For the Raider's stealth needs, even the smaller parts get special attention. Engineers use additive manufacturing, 3D printing, to build lightweight fuel injectors and complex ducts with internal channels that would be impossible to make with traditional machining. Coatings complete the story. Ceramic thermal barrier layers protect hot sections, while radar-absorbing treatments and special surface finishes reduce infrared and radar signatures. Each component then goes through ruthless quality control, microscopes, laser scans, and stress tests, and only the perfect parts move on to the assembly floor. Next up, how those perfect parts are assembled, balanced, and tested before a single engine ever leaves the factory. The B21's turbofan engines aren't built in one go. They start as modules, each crafted and tested on its own. Major sections come first: the fan module, the low and high pressure compressors, the combustor, the turbine stages, and the shafts that tie them together. At the fan station, those wide titanium blades are fitted to the hub and then painstakingly balanced. Even the tiniest wobble could cause vibration, noise, or efficiency loss, all deadly to stealth. A few steps away, the compressor modules are stacked together like spinning discs, each one squeezing the incoming air tighter and tighter as it moves toward the core. Then comes the combustor, lined with special heat shields to survive temperatures over 1,000 degrees Celsius. At the back, the turbine module takes shape, designed to capture that furnace blast and spin it into usable power. Each module heads to a bench testing station. Rotors are spun at high speed to check balance. Compressors are pressurized to detect leaks. Combustors are fired to prove they can handle extreme heat. Turbine blades are checked for cooling flow. Nothing moves forward until it passes. Next comes the final assembly, where everything comes together. Shafts are lined up, bolts are tightened to precise settings, and sensors, wires, and fuel lines are connected. Piece by piece, the modules become a complete engine, ready for the ultimate trials that will follow. Once an engine is assembled, it doesn't go straight into a bomber. First, it has to survive a brutal series of trials that push it to the absolute limit. Inside giant test cells, the engine is bolted down and brought to life. At idle, engineers listen for a clean, vibration-free spin. Then the throttle is pushed forward, airflow builds, combustion lights, and the unit is driven up to maximum rated power, the kind of stress it might see on a mission. Sensors watch every metric: temperatures, pressures, fuel flow, and blade vibration. The real challenge is heat. During hot soak runs, the engine is run red hot to prove the superalloys and ceramic thermal barriers can survive sustained furnace-like conditions. At the same time, vibration monitors check that spinning shafts remain balanced, even at thousands of revolutions per minute. Engines also go through endurance trials, simulating long missions. They're cycled through rapid throttle changes, extreme crosswinds, and sudden shutdowns to ensure nothing cracks or warps. Only after passing every trial does an engine earn its stamp of approval. Fitted onto the B21, it turns a collection of perfect parts into a long-range, hard-to-detect weapon, ready to fly, strike, and disappear. And that's how the engine behind the B21 Raider is built. From exotic alloys to brutal test trials, every step designed to keep America's newest bomber invisible and unstoppable. So, what do you think? Is the B21's engine the future of stealth aviation, or just the start of something bigger? Drop your thoughts in the comments below. If you enjoyed this breakdown, hit like, subscribe, and share it with a fellow aviation enthusiast.